For more than 50 years, no human spacecraft had returned to the moon and back. Then, Artemis II changed that. This mission was not about landing. It was about proving that a modern deep space system can carry a crew out to lunar distance, loop around the moon, and come home safely. And what makes this possible is not just rocket power. It is prediction. Prediction of position, prediction of timing, prediction of how gravity will bend a path days in advance. This is the mathematics of Artemis II, how we aim for where the moon will be, not where it is.
Artemis II launched on April 1, 2026 at 6:35 p.m. Eastern from Launch Complex 39B at Kennedy Space Center. The SLS upper stage first placed Orion into an elliptical Earth orbit, then into a high Earth orbit that extended to about 46,000 miles beyond Earth. SLS means Space Launch System, NASA's heavy lift rocket for Artemis missions. After systems checks, Orion performed translunar injection on April 2nd. That burn committed the crew to a free return trajectory around the moon. At closest approach, Orion passed about 4,067 miles above the lunar surface. At peak range, the mission reached 252,756 miles from Earth, setting a new human distance record. The crew then returned and splashed down at 8:07 p.m. Eastern on April 10th. Total mission distance was reported by NASA as 694,401 miles over nearly 10 days. So this is not only a symbolic mission, it is a full end-to-end flight test in real deep space conditions.
Under all the visuals, the backbone is classical orbital mechanics. First, Newtonian gravity. Acceleration equals minus mu times r over norm r cubed. Here, mu is the gravitational parameter, which is g times the mass of the central body. The vector r points from that body to the spacecraft, and norm r means the distance magnitude of that vector. The minus sign means gravity pulls inward, back toward the center. That tells us exactly how the spacecraft state evolves under a central gravitational field. Second, the Vis-viva relation. V squared equals mu times quantity 2 over r minus 1 over a. In that equation, v is speed, r is current distance from the attracting body, and a is the orbit's semi-major axis, basically its size scale. So for a given orbit size a, speed must rise when r gets smaller and fall when r gets larger. That equation links velocity to where you are in an orbit and to the orbit's size. And third, Kepler's third law. T squared is proportional to a cubed. T is orbital period, the time to complete one full revolution. Bigger orbits take longer. That sounds simple, but timing is everything in lunar missions. The point is this: changing the transfer geometry changes both speed and arrival time. And arrival time determines whether the moon is actually there when you arrive.
Here is the key guidance problem. We do not target the moon's current position. We target the moon's future position at arrival time. Mathematically, we want spacecraft position at final time to match the moon position at final time. A useful first-order estimate is the lead angle relation. Phi equals lunar mean motion times delta t. Phi is the lead angle, how far ahead of the moon's current position we must aim. Lunar mean motion is the moon's average angular speed, and delta t is time of flight. If translunar coast is around 4 days and the moon moves roughly 13.176 degrees per day, then the moon advances by about 52.7 degrees while the spacecraft is in flight. That is a huge angular shift. Miss that timing and your flyby geometry changes immediately. So flight dynamics iterates continuously. Tracking data comes in. State estimates are updated. Linearized sensitivity, often written with a state transition matrix, which you can think of as an error map from now to arrival, maps tiny initial changes to final position errors. Then, small correction burns trim the path. This is why navigation is not one burn and done. It is prediction, estimation, correction, repeated with discipline.
Artemis II used a free return style profile. That means the trajectory is designed so that lunar gravity naturally bends the spacecraft back toward Earth.
In simplified patched conic language, we model one gravity-dominated arc in Earth's region, then transition near the Moon, then continue on an Earth return arc. A useful boundary scale is the sphere of influence estimate. R sub I is approximately A times m over m to the 2/5 power. Here A is the Moon's orbital radius around Earth, m is the Moon's mass, and m is Earth's mass. So m over m is just the mass ratio, telling us how strong the Moon's local gravity region is compared with Earth's. Inside the lunar neighborhood, the flyby behaves like a hyperbolic pass, where the turn angle can be expressed as delta equals 2 arcsine of 1 over e, and e depends on periapsis radius, incoming hyperbolic speed, and lunar mu. Periapsis radius means closest approach distance to the Moon's center during that pass. Practically, this means the Moon acts like a gravity steering wheel. It rotates the velocity vector in just the right way for return. For crewed missions, that geometry adds an important safety layer. If major propulsion capability is lost after translunar injection, the baseline path can still bring the crew home. Apollo 8 and Artemis II are often compared, and for good reason. Both are crewed lunar vicinity milestones, but their mission designs test different things. Apollo 8 in December 1968 performed translunar injection, entered lunar orbit, and spent about 20 hours there, completing 10 lunar revolutions. Its total mission duration was 147 hours. Artemis II in 2026 used a crewed free return flyby rather than lunar orbit insertion. It validated Orion and SLS in deep space, including life support operations, manual piloting demos, guidance updates, and high-energy return. So Apollo 8 proved that humans could reach and operate at lunar distance. Artemis II proves that the modern architecture can do it again, with systems and procedures aimed at sustained lunar campaigns, not a one-time sprint.
From Apollo 8 to Artemis II, one theme stays constant. Spaceflight is choreography under gravity. The Moon is moving, Earth is rotating, the corridor home is narrow. And yet, with good physics and careful guidance, a crew can leave Earth, arc around another world, and return to a pinpoint in the Pacific. This is what trajectory mathematics really is. Not abstract symbols, a language that turns intent into arrival. And this mission is only the beginning. The next arcs are already being drawn.
Thank you for watching. Don't forget to like and subscribe, and comment what planet you think will conquer after our Moon. See you in the next journey.